Hi, everybody. I hope you can hear me. Welcome to this tutorial at AAMAS. And what I'll do here is guide you through for the next 3 hours on explainability in machine learning. I'll stop sharing my video now and put on the slide deck so that it becomes easier and less distracting. So, welcome again to this tutorial on explainability in machine learning. And as the title clearly indicates, it's basically an introduction for the uninitiated. I'll explain what that means shortly. So this tutorial is at AAMAS and it's for 3 hours. Any follow-up material, including links to the video and the recording, will be up on the website. The link is below, okay? Just very quickly, and I'll go into more detail as we get into it. Explainability is a growing and very complex area in AI, and there is a lot of activity in the last few years. Although there were some prescient discussions back in the 80s and the 90s, to be fair. And again, the notion of explanations differs somewhat depending on the area you're from, and correspondingly, it includes different technical devices from interactivity to causal attribution to debugging, to decision boundary inspection and mental state modeling. Okay, so what we will focus on in this tutorial primarily is to consider an overview and interpretability in machine learning, and it's not very technical. Now, to kind of put things in perspective, who is this for? Anybody really with a casual understanding of machine learning is fine. What you expect to get out of it is a bird's eye view of understanding how machine learning decision boundaries work, how they can be probed. What we will cover is, I'll spend a good bit of time on prefacing the area, so preface to explainability in machine learning. I'll talk about concepts and a taxonomy, and actually multiple taxonomies for understanding and positioning explainability in machine learning. I'll go into detail into 2 techniques depending on the time that we have, go into future directions, and with breaks, this will be about 2-3 hours, okay? So that's basically the plan for today. So again, if you don't have a very strong background in machine learning, that's fine. This is not going to be an overly technical proposal. I'll try and give you some perspectives on where exactly the development is happening as far as interpretability in machine learning goes. Now, let's start with it really providing a preface to this area. And as I said, explainable AI, has been around for quite a while. In fact, the KR hypothesis, the knowledge representation hypothesis, explicitly makes reference that the users or the modelers understand what's happening inside the system. But anyway, the way we think of XAI and the way it has burgeoned in the last few years is a fairly recent development. And again, the idea is that humans have a way to understand, trust, and better explain what's happening inside the system. And again, this is primarily motivated by machine learning, although it is a fairly broad area encompassing many different aspects of AI. And what we want to keep in mind is that the added ability does not sacrifice accuracy or effectiveness, okay? So we have a method in mind, and this could be a method for planning or for machine learning. And we want to ideally have this case that, by including or enabling explainability, we don't really lose out on its effectiveness or accuracy. And I guess this brings us to perhaps 2 related notions we want to keep in mind, explainability and interpretability. They are, of course, sometimes used interchangeably, but here are 2 definitions I'm happy with that I think they kind of make sense in the context of the discussion of this presentation. We can think of interpretability as a kind of passive characteristic, okay? It really corresponds to transparency. It really corresponds to the ability to understand what the model is doing. We can think of explainability as something of an active characteristic where the model is explicitly trying to fill the gaps. So the algorithm is trying to explain itself to the human being by trying to get a sense of what is being asked, okay? So the explainability in this sense is a kind of procedure that tries to fill the gaps between its own internal model and what the user is expecting, or what the user takes or makes of the world. So this is a much more richer sense that this is encompassing. Okay, and it's not surprising that philosophically explanations actually touch on many different aspects of human cognition, and it's really about communicating relevant knowledge. Now, if you take into account that AI encompasses machine learning, automated planning, many other areas, it's not surprising that explanation itself has come to encompass many different areas, from machine learning to planning to human-computer interaction to robotics and so on. And in each of these areas, again, it has manifested itself in terms of different technical devices. There's interactiveness, causal attribution, debugging, decision boundary inspection, mental state modeling, and many other things. Okay, so sometimes even a combination of these things, depending on the area you're from. But as I mentioned at the very start, we are going to primarily focus on this idea of understanding or interpreting the predictions of classifiers. So what does this mean? It means that we look at techniques to better understand how the decision boundary of the machine learning system works. And this is useful, even if you're not in the area of machine learning, for a number of reasons, in so much as classifiers and learners will become parts of agent systems. This could be robots, this could be software agents, whatever. Understanding the low-level aspects of these systems, which will presumably involve machine learning, will become important. So this low level of inspection will become important to debug and have an overall understanding of the system. There are, of course, theories of cause, effect, agent interaction, social expectation, and justification. And all of these, as far as I'm concerned, are fairly orthogonal to the more primitive type of understanding of the machine learning decision boundary. Okay, they all sit on top. So you can think of, having a kind of low-level system that is able to deal with perception data, and then you have all of these complex theories of justification and social interaction that are sitting on top, and in a way, one is fairly orthogonal to the other, but nonetheless, it is useful to have a connection. So if there is a way for these high-level theories to connect to the low-level perception data, this is useful in terms of the correctness of the overall system. Okay. It turns out, anyway, as we will see in the tutorial, even this low-level flavor of inspection of the decision boundaries also interactive in nature. And the tutorial really gives a bird's eye view of understanding the essential ideas. And hopefully it suggests interesting directions for you as a researcher to think about, okay? I'll just say that in the interest of simplicity, I'll abbreviate what I'm doing in this tutorial as XAI anyway, but although I've made it clear that what I'm really talking about is interpretability in classifiers in machine learning systems. Okay, so it doesn't really reflect the overall area, but to avoid using new abbreviations and calling it IML or something like that, I'll just call it XAI, and it'll be clear that I'm focusing on interpretability in machine learning. Okay, so for those of you who are not very familiar with machine learning, let me just give you a very quick recap of what the playing field is like. Now, machine learning has been around, since the early days of AI, in fact, and but really in the last few years, it's taken perhaps the majority of the pie when it comes to AI research. And what we're really focusing on are algorithms that are able to pick up properties from data, okay? And they're widely used from predicting heart diseases to advertising to credit risk, et cetera, et cetera. Just in terms of informal notation and terminology, I'll often say model to refer to a machine learning model like a random forest or deep learning or whatever. And I'll use the term approach and method to often refer to the pipeline that we will need to implement to enable explainability. Now, it shouldn't come as a surprise that what you will see in the rest of the tutorial, of course, will involve various aspects of the machine learning models design. So this is everything from input data to the feature space to the parameters. So for instance, in deep learning, the parameters might be the weights and the vectors. It might be the number of layers. It might be the number of nodes, etc. Right? So all of these are critical aspects when we think about enabling explainability, and somehow explainability has to incorporate these different dimensions to work cohesively and properly, right? So this is something we'll have to accept, and obviously there will be techniques that try to abstract away some of these details and give you a more generic view, more functional view of how the system works. But nonetheless, as you get deeper and deeper into it, there will be techniques that try to exploit the architecture and the parameters to give you better results, right? That's just the nature of the game, right? All right, so to just put this in picture, what you're really looking at is a diagram of this sort. So you have input data from which you might extract features, and you have target labels, right? You input to this learning algorithm to construct this function. And now you have a new data point, and what you're interested in is what is the label that is going to be accorded to this new data point, right? So that's the essence of, so let's say, prediction in machine learning. Now, what's the issue here? Of course, because they work on the data, there is, of course, a bit of algorithmic designing, but in the end, many systems like deep learning systems are essentially black boxes. You set up the architecture, you set up the parameter learning space, you feed in the data, and you get a system that does something, but you don't quite know what's happening inside these systems, right? A clear example of this is something like a convolutional neural network. Now, there was a very famous example from a few years ago where they kind of showed how brittle these systems are. So what you have is you can have an image of a panda. It's clear that it's a panda to you and me. You first notice that it is actually predicting panda with a very low confidence. Then you add a bit of noise here, which is the one in the middle, and you get an image that to you and me is essentially identical to the first image, right? It is still a panda, but now the system is saying that it's a given with very high confidence, okay? So this is clearly a problem. And if you think about a self-driving car with this amount of, this amount of lack of robustness, it is clearly a problem, and it can be dangerous, and we want to avoid this. So we need to understand what the system is doing. So this brings us to, I guess, taking a step back and thinking, in terms of the classic machine learning models, what do we have in mind, right? So on the one hand, we have transparent models, and I'll describe them in a bit more detail shortly. And then you have these opaque or black box models, right? So from my description, clearly a deep learning system is a black box model in that regard. And for these kinds of black box models, you need to have some additional ingredients fit in to understand what they're doing. So let's look at transparent models, okay? In general, I suppose you could use the term transparency to mean that it stands for some level of human understanding of what the system is doing. Now, there are certain machine learning models that I think fairly unambiguously we can all agree that they're transparent, and we'll see how exactly they mean in a follow-up slide deck. But for now, we can think of transparent models as having possibly three characteristics, okay? There is the idea that you can simulate it, the idea that you can decompose it, and the idea that the algorithm itself is kind of transparent. Let's see what this means. So the first one is that you're able to simulate it, okay? So I will use the example of a decision tree for all of these characteristics. And what this means is that you can kind of really think about the model's internal reasoning, in your head, right? So a classic example is if you have a decision tree that is deciding whether you should take an umbrella, And it might be something like if you're protecting yourself from the rain, right, and it is raining today, then you want to take an umbrella, right? So it's you, if it's not raining, you wouldn't take an umbrella, and if it is raining, you would take an umbrella. And this is not atypical to how we might decide to wear a certain kind of jacket or take a certain kind of shawl, and taking an umbrella, right? So that's the first characteristic. The second characteristic is that it can tease apart different parts. Now, this is also true with conventional computer programming, that modularity and decomposability are interesting characteristics which people regard as necessary to avoid code obfuscation, right? So, to write clear code, it is understood that you will come up with a nice modular way of thinking about the overall pipeline. So similarly, in machine learning models, when you think about transfer machine learning models, you ask yourself, can I break it apart? And to an extent, again, if I thought of a decision tree, this is true, because I could look at a subtree, and certainly in that context, what the decision tree is making often makes sense, right? So for instance, if I look at a subtree where I'm deciding whether to, for instance, wear a business suit, which might be in the overall plan of what will I wear today to go to work, that particular part, again, will make sense because it might be based on the kinds of meetings I will have in the day, right? So modularity and decomposability do make sense also in the decision tree. And finally, there is the idea that is the algorithm itself transparent? And again, with the decision tree, this is true, but because I can traverse the tree, which is really like parsing the algorithm for the decision, and it's all making sense to me. Okay. Now, keep in mind that this all looks good in intuition, but in practice, if you have a decision tree that's extremely complex, it is not any more transparent than say a deep network, right? Because it might have so many nodes, and if it is also defined over a very complex feature space, you might run into trouble. It won't be much understandable. It won't be very understandable. So transparency criteria is really not airtight. And what you want to think about is post-hoc explainability, okay? What is post-hoc explainability here? What we really mean is that you have constructed a machine learning model, you've trained it, you are ready to go, and these are techniques that step in at this stage, okay, to give you some perspective of what the model is doing. And at a very loose level, we might divide them. This is again from the technical aspects of these methods. We might divide them into so-called model agnostic techniques and model specific techniques. And what that really means is that is a technique designed for a specific machine learning model in mind, so a random forest, deep learner, or is it something more generic that purely works at a functional level? So looking at the input-output, behavior of the algorithm, is it able to construct something? And as we will see, model agnostic techniques are very interesting, and they are very popular, obviously, because you can apply it to a broad range of different models, machine learning models. Okay. Now I'll make one point that precisely because with transparent models, you could run into the issue that these models are very, very large. In the case of a decision tree, that might involve thousands of nodes and hundreds of different features. Post-hoc methods could also be applied there. Okay, certainly model agnostic methods could be applied there. So they become useful to you regardless of whether you have chosen to do a transparent model or an opaque model. One other angle that will become interesting and important in terms of understanding explainability techniques is this aspect of local versus global, okay? So local explanations are such that they rely or they're based on a single instance or a set of instances. So what they really do is that they inspect the decision boundary at a certain data point or all the data points that are in the vicinity, okay? Global explanations, on the other hand, they try to summarize the model's overall functioning. So this obviously becomes important because in certain cases, global explanations are obviously attractive because you know how the overall model works and you're not stuck in some local region, right? But precisely because of this, global explanations can be difficult to achieve in some cases, okay? So let's take a step back and we'll take a few minutes to reflect on these key takeaways that are good to reflect on. I'll let you take a few minutes to inspect this. I'll try and answer maybe just the last 2 points, right? So reflect on how a model that you can simulate in your head could lose its transparency. And we have discussed this. We are thinking of a decision tree with hundreds of nodes. And clearly, even though in principle, you can simulate such a model in your head, you can't really do this, right? For a tree with hundreds of nodes. And let's look at the last question where, what's generally better? Is it a local model specific or a global model agnostic? Although I haven't gone into the advantages and disadvantages, clearly model agnostic is better because you can apply it to a larger number of models. And as we just discussed, the global explanation feature is a good thing to have because you're not stuck on some local region. So the latter, if it is possible to achieve it, is obviously better, right? All right, so let's now, before we go into the frameworks and so on, let's just spend a few minutes to reflect on the importance of this area. Okay, so why do we care about it? And we know why we care about it, because machine learning models are being used widely, and you want to talk about, the fact that you understand how the decision was taken. But let's give this a bit more clarity. Okay, let's try and identify the dimensions in terms of which this becomes important. So one thing, for instance, is you could have a wrong objective, right? So recall that what the algorithm is trying to optimize is some characteristic that the human has decided is what the model should be trained for. But if this is slightly misspecified, this could lead to a model that's doing something that's unintended, right? There is also this issue that the feature space is something that's designed by humans. It could be either picking up on features that you don't want to pick up on, like, for instance, gender or race, or even if you think you have eliminated these features, you could have other correlated features to this, right? So a simple example is, let's say you have tried to remove gender as a criteria for your model, but it turns out the school that the individual has gone to is already an indicator whether they're male or female, right? And in this case, you have not eliminated the column for school, but inadvertently it reveals information about the gender, and you want to make sure you pick up on these correlations, and explanations can help in helping you understand what the model is doing. There is a very important issue about what is called as distribution bias. Essentially, what is happening is that you train the model in a specific context with respect to collected data, and then you go and deploy it in the real world. And then you notice that what is actually happening in the real world is very different from the training data, right? So this is an example where you might have a vision system that works really well in the lab, and then you go and put it on a self-driving car, and it is chaos, right? So you want to pick up on these kinds of things. There is also the issue of user control. I mean, as humans, obviously, we want to be able to tweak the algorithm, provide input to it in various ways. And in this case, explanations can help because they can tell us what needs to change in the model for it to behave in the way we wish it to, right? Generally, there's the issue of trust as well as legal imperatives. So it is helpful for a number of reasons for us to trust the model, as well as it is helpful if for GDPR and other reasons, if the algorithm is able to provide explanations of what it's doing. it improves human insight, and again, it goes back to user control. So all of these are great reasons for enabling interpretability. Okay, so again, to summarize, the key concerns in machine learning models: we want to think about correctness and the objective function we provide. We want to think about the distribution drift and robustness. We want to pick up on correlated features, especially protected attributes like gender and race, and catch bias. We want to obviously improve the model and make it perform really well, both on the training data as well as in the real world. We might want to transfer the insights we learn from one model to another situation. And ultimately, in terms of trust and comprehensibility, human comprehensibility, it becomes really important to have to enable interpretability. Okay, so these are all the great reasons. And this brings us to what exactly interpretability is, and we've kind of skirted around the issue through this presentation. But the idea here is that you are able to identify features that have a meaningful significance on the output. You want to understand how the decision boundary works. You want to catch problematic aspects, figure out if the decision boundary is overly relying on certain data points. So for all of these reasons, right, understanding the decision boundary becomes an important aspect. One thing I will mention very quickly is that there is this general, I think, misconception that in some sense, interpretability is a heavy price to pay. It might affect the performance of the model. Now, this was perhaps in some sense intuitively accepted in the early days of XAI, but I don't think people are really convinced this is always true. What is clear is that when there is a structure present in the data and the features are interesting and important to understand what the model is doing, then transparent models can become extremely useful. Now, the one place where more complex models like deep learning might help is if the training space offered by these models allows highly nonlinear and complex decision boundaries. Then it can be helpful to have a model with a very complex parameter space, very high dimensional parameter space. So in these cases, clearly, complex models help, or opaque models help. But generally, there has been a lot of development also with transparent models, or what we also call as hybrid models, encompassing aspects of transparent models and opaque models. And so this gap is closing. This was all reflected in an early plot from DARPA, where they kind of plotted, so to speak, different models and where they fit on the so-called prediction accuracy versus explainability axis. But this is not really a sensible plot. As I said, when the data is structured, it is useful to have models that can directly leverage this and provide some insight into it. And this is also not based on any real data, right? For instance, we have no real way of really quantifying explainability. So it's not quite clear what exactly this is supposed to mean. And prediction accuracy can also mean different things, especially when you want to consider the fact that you want AI systems to be applicable in a broad context and not just with certain label data for which there's a lot of data on, right? So this is complex space to measure and compare methods on. And in that regard, this plot isn't really to be taken at face value, okay? Let me stop here and give you a few minutes to reflect on the key takeaways and think about, these different questions. And again, the response to these questions are present in the discussions we've just had. Perhaps one thing that I can quickly speak up on is the first question, and what benefits does XAI offer? And as I said, for the longest time, we have somehow not really addressed some of the issues that occur when training machine learning models, from distribution drift to having wrong objectives and so on. Although, of course, there is academic research on some of these questions addressed in a very narrow way. Explanations offer a more accessible way of looking into these issues, okay? Let's now turn to, again, who benefits from explainability. And this is a range of possible stakeholders. This could be anything like you and me, a data scientist who's trying to understand the model, debug it, and improve the performance. You could have a business owner who's trying to understand and see its fit for purpose. In banks and other organizations, you have model risk analysts who look to challenge the model and approve it. You could have a regulator who's checking the impact of this algorithm on the consumers, and then you have the consumers themselves who are assessing things like, what's the impact on me? How can I change the decision that was taken on my behalf? Okay. This brings us, I suppose, to what are good criteria to evaluate XAI techniques on. And again, because there is some amount of intuitiveness and lack of precision in how exactly you can measure some of these quantities, we'll have to keep it at a more high level. There is research emerging on trying to crystallize and quantize some of these notions, but to a large degree, right? What you're really looking at is perhaps user studies to better assess and compare different models. So the kind of things we care about is comprehensibility, right? How easy is it to understand, for us to understand a certain technique? Especially when these techniques involve some kind of simplification or construction of a more complex model as a simpler model. You might look at things like fidelity and accuracy. So is it really capturing the model well? Is it really as accurate as the more complex model? Is it scaling as well as the more complex model? And you also think about generality, right? Does it require, can you apply to any of the complex models? So do you need the complex model to be trained in a certain way or taking a specific shape before you can apply some of these techniques, right? So these are different ways you can compare XAI techniques. And as I said, because some of these quantities are difficult to, some of these properties are difficult to quantify, we are left with more informal arguments about what all of this means, but nonetheless, they're extremely helpful, at least at an intuitive level, to argue why one technique might be better than the other. The other kind of facet to think about is the types of explanations we can offer, and these are fairly self-explanatory to the most regard. You might think of explanations that provide, let's say, natural language text that tell you what the model is doing. You might think about plots and other kind of visual cues to help you understand what the model is doing. As I mentioned, local explanations versus global explanations are two kinds of explanations that either focus on a specific region or a specific data point versus the overall model's behavior. Another way you can kind of get a sense of what the model is doing is explanations by example, which means that you get a representative data points that tell you these are the prototypical examples that really tell you, and their values, which tell you how the model works. For instance, a student typically just before graduating who has applied for the loan will generally be approved. So this is an example. By looking at this example, you kind of can assess or at least take a guess at what is important for getting a certain prediction. Explanations by simplification is a strategy by means of which a more complex model might be reduced to a simpler model to understand what it's doing. And feature relevance explanations are perhaps the most classical form of explanations, where you mainly tell you which features matter the most in the decision. So for instance, if you see salary and age being the biggest factors for understanding whether a person's mortgage application is approved, then this is indicative that by looking at these two features in a certain data point, you should be able to assess whether the mortgage application would be approved or not, right? So these are the possible types of explanations that we have. So again, I will give you a few minutes to reflect on the key takeaways in terms of the material we just covered. And I'll just answer the first question here. to convince a non-technical person what type of explanation might work best. Now, keep in mind that if you think about the different categories we saw, it really depends on what this non-technical person is looking for, but presumably something like a text explanation that involves perhaps either a local characteristic or a prototypical example might help a non-technical person grasp what the model is doing, right? I mean, this is up for debate. I guess you could also argue visual explanations are interesting, but if the visual explanations are statistics plots, right, this is not very helpful for a non-technical person. Obviously, simplification doesn't help a lot. So it really has to be either a textual explanation with, if it is visual, it would have to be something intuitive. Certainly explanations per example could be helpful, provided the data point is not given in full, but a certain aspect of it is provided, right? So that's something to keep in mind, okay? All right, let's look at some open questions here. This is up for debate again. Argue how XAI evaluation criteria differs or is the same from good ML criteria, right? So good ML models, you typically look at accuracy, you look at scalability, and again, this is something we have as overlap with the XAI criteria, but then, you know, in XAI criteria, you also care about things like fidelity, as well as comprehensibility. And I suppose you could also argue comprehensibility is an important feature in a good machine learning model as well, right? So that's something that's worth reflecting on. This is a question I think that often comes up on various forums. You know, if you have a medical system that's giving you 98% accuracy, but it's really doesn't make, is not understandable by anybody, including the clinicians, versus you have a transparent model that only gives you 88% accuracy, what would you prefer and why? Some would argue that obviously the more the model offering higher accuracy is better, and perhaps this might make sense if you have an additional layer of intervention where the human doesn't blindly act based on this high percentage, but reflects on it, because usually a human clinician would be able to justify why a certain aspect is important or significant. And if a system is unable to provide this, precisely because in cases where things could go wrong, we should be a bit careful, right? So if it's a first line of defense where further tests can be conducted based on the fact that you know, a certain individual is labeled as high risk, then that's fine. But to blindly act based on this accuracy without knowing how the model works is a bit risky, right? And looking at the last question, if you think about an ensemble of different transparent models, does it become transparent? If you think about it, it's not really the case that this is always true, right? In fact, most likely it is false. A good example is something like a decision tree, and this, in fact, becomes a random forest, right? And a random forest is not really transparent because depending on the number of trees and depending on the decisions internal to those trees, it's hard to understand what the model is doing based on majority voting, right? So that's it for now. This is the bibliography for the first bit. So what I will do now is I will pause the recording. Let's take a quick break and come back to the second bit, okay?